introduction is on Mr. Oliver Wirth. He's the CEO of the Bareiss test equipment based in Germany. Let me give you about his background. After studying the photonics at the University of Applied Science in Holland in Germany, Oliver initially worked in the medical and space industry. In 2017, he took over the management of the family-owned company Bareiss in the third generation together with Catherine Shen. As head of research and development, he brings his expertise and vision to the development of new technologies. His focus is on true innovation in metrology to address open questions and provide new opportunities for industry to better characterize materials. As managing director of one of the leading test equipment manufacturers, Oliver is also involved as a co-chairman in the National Standards Committee of BIM for physical test methods on rubber. He is also a member of the ASTM committee and other national and international rubber industry associations. So let's welcome Oliver Wirth to make a presentation on the Bareiss Introduction to World of Precision.
Well, thanks, Param, for the nice introduction and for the possibility to share some information about our company and the topics we are currently working on. Welcome to today's session about advanced material testing, and welcome to the world of precision. First of all, I want to give you a quick overview about today's agenda. I'll give you some background information about our company, including the product line, the ISO 17025 lab, and give an idea about the importance of the specific quality of our products. Within the context of the hardness session in the second part, we will have a closer look into the hardness topics and the applications as well. So let's go back in history and see how it all began. Even as a child with limited resources, our grandfather Heinrich Bareiss had the technical skills to build models that could fly and drive. After training as a mechanical engineer, he joined the Navy and spent the next 2.5 years on a submarine during World War II. While spending the time on the water in the submarine at great depth, Heinrich came to the realization that the study of materials was of great importance. In 1954, Heinrich Bareiss' vision to start manufacturing mechanical hardness testers became a reality. The company was founded in Upper Swabia, Germany, in the basement of a residence, which is only 100 meters away from the headquarters nowadays. As you can see, Bareiss originally comes from hardness testing and made a lot of new inventions to the specific world. It all started with the mechanical durometer on the top left, followed by a test stand in 1961 and the very first flexible tabletop devices in 1972. The corresponding up-to-date products can be seen on the right. But how does the company look like today? I just mentioned that the company was founded in 1954 and that we are a family-owned business in the third generation. Together with my cousin, Catherine Shen, I am the managing director of Bareiss. We have 4 subsidiaries, including the location in Hong Kong, and we have a production area in Oberdischingen, Germany, of about 4,000 square meters. One of the keys is the high in-house fabrication rates of almost 90%, which gives us the possibility to make quick changes in customized products and so on. We have a lot of patents and obviously lots of customers worldwide. So summarizing, we are a company with a high passion to develop new test methods in a long background of experience. In combination with our ISO 17025 accredited laboratory and the membership in various standard committees all over the world, like for example DIN in Germany and ASTM in the US, it is the best combination for you as a customer to get more information about your materials. We are really dedicated to develop new test methods and to standardize them. We do have our own subsidiaries in China, in Taiwan, and Canada. But besides these locations, we have lots of resellers and distributors, as well as service partners all around the world. We are located in 35 countries to offer our best support to you, so we are your partner worldwide. To give a quick overview about our product portfolio, I listed the main products on this slide. Besides these ones, we also have products for sample preparation like punching presses and cutting devices, and also other physical test products like compression set and so on. On the next slides, we go a little bit more in detail of the different categories that are shown here. It is hardness, rebound resilience, abrasion testing, and rheology. Let's come to the hardness section. In this line, we offer all test methods ranging from 000S to over Shore A to Shore D, as analog devices, analog durometers, and digital durometers as well. But we also have the flexible tabletop devices for your laboratory where you can have the test methods from all the Shore ranges up to all the IRHDs and even VLRH. And this is completed by various check devices that can be seen on the right, including test blocks that we are also delivered together with ISO 17025 certificates. In the rebound section, there are basically two categories. One is the ball rebound tester, which can be used for elastomers, but the main usage of this device is for foams, as you can see on the picture. And we do have the so-called choke pendulum. This can be also purchased including a heating module and all the standard accessories. This is the classical DIN abrasion tester on the left-hand side, including a cleaning device, but also available as a more advanced test method, including a heated drum. So that means the drum itself can be heated from ambient temperature up to 100 degrees Celsius. And last but not least, we do offer the rheology products, but also automized machines ranging from a simple hardness and density tester up to a completely automized laboratory. For the rheology products, we will get more information in the next two sessions from Thomas and Henry. So let's come to the laboratory. Together with the PTB, which is the highest national metrology institute in Germany, Bareiss created some of the most important standards in the field of hardness for rubber and plastics. For example, the calibration standard 18898, which is nowadays known as the ISO 48-9, VLRH, and many, many more. The AKKS is the German accreditation body for the laboratories following the ISO 17025. But every country has their own national accreditation body. As they are following the same standards, they are within a network of mutual recognition agreements among accreditation bodies. And this is mostly visualized by the logo, the blue logo, left of the DAKKS logo here. So therefore, they can be seen as equal quality accreditation bodies. In Germany, for the DAKKS, the accreditations are carried out mostly by the PTB. So for you, the best combination is to purchase devices from a manufacturer that also has an ISO 17025 accredited laboratory. But be careful. ISO 17025 lab does not automatically mean that this laboratory can perform all ISO conform certificates. It's absolutely depending on the scope. If you request a quote for an ISO 17025 conform calibration, which honestly costs some extra money, please definitely ask for the scope in advance or have a look into the accreditation certificate on your own. This is what you can see here. Usually you can find it on the website of the offering company or definitely in the database of the accreditation body. So please be aware that you as a customer also have the responsibility to choose the correct company. Otherwise, you will be in trouble at your next audit. Just one slide about measurement uncertainty. I don't want to bore you with this one, but it's necessary to know what is the difference between an ISO 17025 laboratory and a normal calibration lab. So uncertainty, first of all, seems to be a negative word, but actually it's not. It does not mean being unsafe when measuring. It is paradox, but the uncertainty provides certainty to the conformity. What does that mean? So every value, every reading that is within the green zone is within the conformance zone and totally correct. There is no discussion. It is correct. The values that are located in the red zones are non-conform. There is also no discussion, so they are out of tolerance. The difficult part is the yellow zone, where we cannot definitely say that the values are correct and conform or even not, even if they are within the given tolerances. So the tolerance zone is given by these two lines here, specification zone, and we have the tolerance, and even if values are within this tolerance zone, you cannot say, because of the measurement uncertainty, if the measurement is correct or not. And the goal is to make this yellow part as small as possible. And this is also what you can see on the in the scope of the accreditation of the accredited laboratories. You can see the uncertainty because accredited laboratories have to calculate the uncertainty, and the smaller this uncertainty is, the better the laboratory and the better for you as a customer. Let's come to the quality of our devices. There are a lot of different hardness testers on the market from various manufacturers. Some of them are very cheap, so your question might be, for what reason I should spend more money on a durometer? What makes the difference? Well, the answer is quite simple. The readings are more precise because of the high quality components we are using. Then we have very highly skilled employees that are professionals in building hardness testers for some of them for more than 30 to 40 years. The springs inside a Bareiss durometer get a very special treatment before they can be used. This is necessary for long-term stability of the equipment. And even the ball bearings are handmade for every durometer, using different ball and bushing combinations. And this will reduce the friction to a minimum and therefore shows exact readings, even if you have floating materials. So in this video, you can see a durometer from one of our competitors on a check device. By putting the weight on the left onto a defined position, you can double check if the value shown on the durometer is correct or not. What catches our eye is that every time we tip on the check device, we will get different values. And this is due to the friction inside of the durometer. Now we do the same on one of our own durometers, and you will see a completely different behavior. Every time we tip on the check device here, the needle comes back to exactly the same value after swinging around it. Now you might say, okay, this is probably a nice to have feature, but I will show you the importance on the next slide. Just wait for the video until it's finished. Okay. What is happening with the hardness value while taking the measurement? So this diagram shows you the hardness behavior of one single measurement over time. So you can see time in seconds from 0 to 3 seconds, and the hardness in Shore A values ranging from 38 to 48 in this scale. Watching this result, we can make two perceptions. First, if you would measure this specific material with a low quality device, you would measure around 46 Shore A, which is the maximum point here. With the Bareiss device, you can get the real value around 39 Shore A. This is a huge difference of 50%. And second is that measuring at 1 second, which is part of the ISO 868, is not very reproducible because we are located at a very high gradient. So by varying the time around 1 second, you will have different, highly different readings. So from 0 seconds to 1 second, you have a difference of about 10% between the first value and the 1 second value. So better use 3 seconds because the gradient is not so high anymore. So this behavior happens normally so fast that you cannot see it with your eye, but it is definitely there. So let's come to the hardness session. What is hardness? The definition is that hardness is a mechanical resistance of a material or a test piece to the mechanical penetration of an indenter. Let's see in an overview the different scales that we have. On the left side, you can see all the multiple Shore variants that are available. As you will see on the next slides, they are used for different hardness ranges and therefore different sample geometries and materials. They all follow a linear scale from 0 to 100 and are good for flat surfaces. We will see later on that Bareiss developed Shore A and Shore D measuring heads that can be used for all kinds of geometries, which is a huge improvement and help to many customers worldwide. On the right side, you can see the IRHD scales, which is normal, hard, low, and micro. They are usually used in tabletop devices for production samples. So this is one of the main differences that you can measure on curved surfaces, besides the measuring devices developed by Bareiss. With 30 seconds, the measuring time is very long compared to a Shore variant, and the official micro version is available here, while it is not in the Shore scale. Once again, a short visual overview over all the hardness scales. First of all, we have 4 different IRHD methods. For very soft rubbers, Bareiss introduced a standard some years ago, which is called Very Low Rubber Hardness, VLRH. This test method gives the possibility to measure below IRHD normal with a very high differentiability. So you have 100 readings while you have just some readings, some values on IRHD low. And we have the Shore methods. The main scales are Shore A for rubber and Shore D for mainly plastics. Means if the sample is harder than 90 Shore A, Shore D scale should be used. The zeros are mainly for foam-like materials, and there is a micro scale in the same hardness region than Shore A for thinner specimen, but this method is not used too much in the industry. Therefore, Bareiss invented an alternative to this method, which is called Micro Shore A, Micro Shore B, respectively, and is directly comparable to the real Shore A and Shore D values. But most of all, what you are interested in, or what the rubber industry is interested in, are the scales Shore A, IRHD-N, IRHD-M, and the Shore A on curved surfaces and Micro Shore A. The main organizations developing standards in this technical section are called ISO, International Standard Organization, and the ASTM, American Society for Testing and Materials. 3 years ago, ISO decided to group all hardness standards for rubber and plastics in the ISO 48 family. To make it easier for you, I wrote the main topics of these standards right next to them. The American analog to the ISO 48-4 is the ASTM D2240. And for plastics, there is the ISO 868. I will point the differences later. For the sake of completeness, you can see the DIN 59 or ASTM D2583 respectively, which covers the barcode hardness. This is even harder than Shore D and mainly used for composites like PCB materials and so on. On the next 2 slides, I will show you the differences between IRHD and Shore when it comes to sample thickness and the indenter geometry. So we have IRHD starting from an indenter size of 0.4 millimeters, going up to an indenter size with a diameter of 5 millimeters for IRHD-L. And you can see the sample thickness ranging from 2 millimeters for IRHD-M up to 10 millimeters for IRHD-L. The ones that are mostly used in the industry, in the rubber industry at least, are IRHD-M and IRHD normal, like I mentioned before. So this is the same slide than before for IRHD, but this is for Shore. So you have here all the different indenture geometries and the sample sizes for all the Shore variants. Once again, the most important for you in the rubber industry is probably Shore A, which has an indenture with a truncated cone and 35 degrees of angle. And the sample thickness should be 6 millimeters minimum. The next thing I will show you is the difference of applying the force onto the indenture between IRHD and Shore. At IRHD, we have a dead load system, while we have a spring inside of the Shore measuring heads. At IRHD, we have 3 forces, or 4, depending on how you count them. And one is the force on the foot, which is the pressure plate. Then we have the contact force, which is the force at 0 degrees hardness. And the indenting force, which is applied onto the indenter after 5 seconds of contact force. And all these forces, they result in the total force. On the other side, with Shore measuring systems, you have springs starting from 764 millinewton up to 44,450 millinewton, with contact forces starting from 250 grams up to 5 kilograms. And these forces, they can either achieved by hand or using a test stand. So now we already talked about the geometries of the indenture, we had the forces, and now the third thing, which is very important, is the indentation depth. And here you can see the main difference between IRHD and Shore. While we have a linear system in the Shore scale, we have a nonlinear behavior with IRHD. The indentation depth, which is taken here on the right side, for example, the 2.5 millimeters, this is a system like it is used in Shore A, but there are also other ones ranging from 1.25 to 5 millimeters. Let's come to the last section, which is the application. It is very important to know what a hardness tester can do, but even more interesting and helpful is to know the limits of these devices. So in other words, what your durometer cannot do. So here we can see that we can measure with a durometer, with an analog one, on flat surfaces with thickness of above 6 millimeters according to the standard. What we cannot do is measuring on finished parts. Once again, how can we use a durometer? The only way to achieve an accurate and correct reading is to understand the limits of the devices, like the following. You have to measure perpendicular to the sample surface. The sample size or thickness has to be in the range which is mentioned in the standard. Here it is Shore A for 6 millimeters. You can only measure on the hardness on flat and parallel surfaces. So for example, O-rings cannot be measured. And you have to read the result after a certain time, because your material can be floating, can be a floating one, and also the quality makes a difference, like we've seen in the video before. So we just learned that we cannot use the analog durometer at all times, and that sometimes it's very inaccurate to measure the hardness. From this, we made 2 subsequent developments that were all patented and They are often copied. You will find the Bareiss developments all over the world. For a more accurate measurement on the standard buttons, you can use a digital handheld durometer, which can be seen on the left side, with timing included and also a hand grip around it. If you push it down to the sample, it has two methods. Push it down with the correct force on the one hand, because there is a spring inside, and push it down to be perfectly perpendicular on the sample surface. But what can I do if I have finished parts or thin-walled materials, but I still want to use the Shor scale? This can be answered using the right side of this slide. We were the first one to develop a completely modular tabletop device with interchangeable measuring heads and various sample holders. We can deliver the whole range of test methods that are available for rubber and plastics, starting from IRHD, Shor, and VLRH. Even better, the full range can be purchased, including an ISO 17025 calibration certificate, which gives you the maximum reliability on your measurement results. But once again, the ones that are used in the rubber industry are mainly the ones that are shown in the red boxes here. What is so special about our Digitest 2 that we've seen just in the slides before? Like I mentioned, you can also measure on finished parts that can be even convex or concave. And this is a development made by Bareiss in the year 1972, when we saw a strong need for this ability in the Shor scale. The result, Shor AB0 and Shor DC D0 respectively. A good, reliable, and not least reproducible result can only be achieved by two factors: the measuring device and the correct sample preparation. You can have the best hardness tester and you don't get good results if you don't have the right sample fixture. Therefore, we offer a wide range of fixtures. For example, here you can see one for wires, one for hoses, O-rings, and a universal bench-wise. Over the decades, we made a vast number of customized fixtures, and we offer the service that you can send the sample to us and we consult you with the solution. This is included in our service we offer. It is even possible to add small automation to your Digitest, also to existing devices by an easy upgrade. Two of these can be seen here. The RotoFix on the left side offers the capability to measure a various number of samples without user intervention. The third generation of Bareiss, on the right side, will do a laser centering of O-rings, because it is very important to measure the hardness on O-rings at the highest precision. Let's come to the next application. For some applications, it is necessary to know the physical properties apart from ambient temperature. In this case, it is helpful to test the hardness inside of a temperature chamber. We developed a system which integrates the hardness tester into a temperature chamber to reach temperatures ranging from -70 degrees Celsius up to 180 degrees Celsius. To reduce the temperature influence on the measuring system itself, all parts that are not necessarily have to be inside of the chamber are outside, such as, for example, measuring head, pickup bracket, and the electronics. To reach a homogeneous temperature inside the sample, it takes a certain time, depending on the material and the geometry itself. Therefore, the chamber comes with an automation and a smart software to set up a test sequence. This will make it possible to control both the chamber on the one side and the hardness tester on the other side. A very easy and intuitive system to use. This is an example of 5 different tire compounds measured for one of our customers. The x-axis is ranging from plus 60 degrees Celsius on the left side to minus 40 degrees Celsius on the right side. And you can see that the behavior of these 5 compounds is totally different. We have materials that are very soft in the range of about 60 degrees Celsius, for example the blue one, the dark blue one, but will get very hard at low temperatures, almost 90 Shore A. While there are also materials that have an increase of the hardness of only 18 Shore A values, for example the green curve here. So makes a huge difference. Let's come to the second and last application for today, which is hysteresis. At the hysteresis measurement, we take a dead load system and we apply a force onto the material, and then we measure for 99 seconds, and then we reduce the major load and we measure for another 99 seconds. So we have a loading curve on the very left side, and then we have an unloading curve on the right side. So this was measured on the same material with different heating times. So the materials, they were cured to 100% or only 50% time, and therefore you can see different loading and unloading curves here. This can be used to analyze and decide if the product quality is good enough before putting it into production. It accelerates the process of decision making and prototype approvals. It saves, of course, energy, time, and wastage, and it increases sustainability of the process. Thanks for joining and listening today to my presentation about hardness and our company. And I hope you got some ideas and suggestions, maybe what you can use, what you can do with hardness, and maybe this encourage you to do more on hardness testing than you did before. Thanks a lot once again, and looking forward to the presentations of Henry and Thomas as well for the RPA Ultra. Thank you. Goodbye.